Here's a picture of me and my Bearcat card. Question 1. Consider for all integers n, if 6 divides n, then n is equivalent to 0 mod 3. Describe this statement using direct proof, proof by contrapositive, and proof by contradiction. So this statement is equivalent to for all n in z, 6 divides n implies 3 divides n, where 6 divides n can be p of n and 3 divides n can be q of n. For direct proof, first we let n be in z, and we assume p of n. And then we use these rules to prove q of n. So the conclusion is, since q of n is true based upon the assumption p of n, then the statement is proved. For proof by contrapositive, we also let n exist within z, and assume, for this one, we assume not q of n, and then we use rules to prove not p of n. The conclusion is, since not p of n based on the assumption not q of n, by the contrapositive, q of n is true based on the assumption p of n. So the statement is also proved in this method. Through proof of contradiction, so first you take the not of the entire statement. So if we were to do not of for all n in z, p of n implies q of n, this would be equivalent to there exists n in z such that p of n and not q of n. So for 1, you suppose the implication is false, like we did above. Then there exists n in z such that p of n and not q of n. So 2, we use rules to prove that a contradiction exists and that this is impossible. So for the conclusion, we find that such an n cannot exist, and the implication is true for all n in z. So the original statement would be proved. For question 2, make a true statement about absolute values of real numbers that can be proved with an example. So for our statement, we will do there exists x, y, z in real numbers such that the absolute value of x minus z is less than or equal to the absolute value of x minus y plus the absolute value of y minus z. So I'm not going to go through the entire proof, but I have it written out here. So this proof can be solved by example because it is in the form there exists x, y, z in real such that p of x, y, z. Only one example is needed to show p, x, y, and z is satisfied. It's really all because of the there exists statement. Since it's there exists, you only need one specific example. For number 3, make a true statement about the complements of sets that cannot be proved by example. So for this one, I will do the statement, let A and B be sets. Then the complement of A intersection B equals the complement of A union B. So again, I have the proof down here, but I won't read through it for time's sake. This proof cannot be solved by example because A and B are sets, and there's not a qualifier in the beginning, like there exists sets A and B such that. Since that's not there, this must be proved for all A and B, so you can't just use one specific example to explain it. Thank you.